Hello again. April 22nd, 2024. Problem 7 of the last section in chapter 3. Even the first sentence, or the second one, we have to show a lot of stuff. First, L mark contains L, then it has index n, then it depends only on the right coset, gamma 1 of level n, and finally T has order D. That's of course a critical point to check that we get the right Tn. But let's get started with them one at a time. First, L mark contains L. So the idea I have is that if we have an element in L, then it's mapped to 1 divided by n alpha gamma p in L mark. And I believe we can go backwards here. No, that's not right. Or maybe we should go backwards from P. Yeah, we need to find a P that it so we are given a P naught in here. And then we must find a P so that this guy equals P naught. And the inverse, alpha lies in the general linear group with integer coefficients and has determinant n. And then the inverse is 1 divided by n times beta, where beta has integer coefficients. That's the usual formula for getting the inverse of a matrix. So let's see what we can do. P equals n gamma to minus first alpha inverse P naught, and this is beta P naught, while I'm recording, I'm not quite aware of the logic here. My idea was now we are finished, but I don't understand presently why we are finished. So we have a p. So we start with a p here, and then given a p naught, then we take this p, and when we operate with this guy on p, we end up with p naught. Right. So that was A. B, it has index n. That's pretty obvious, I think, because the determinant of equals 1 divided by n, so it has index n. Using, of course, its they are sublattices, so we have a sequence of lattices, and the index here is n squared, and the other index is n. Yeah, that's B. Now C, it depends only on right cosets of gamma 1n. And then let's take the inverse of alpha. Now we can't call it beta, gamma, so it's called capital A. Well, let's operate with gamma to minus first as well. Then this guy must have determinant unity. I don't know where this is leading. If we have this guy, and then beta equals gamma mark alpha with gamma mark in gamma 1 of level n, then they should give the same lattice. I was at a loss here. Now the telephone has called and I have had to do a small stop. I've had to do a few things. So I'll just make a break and then see what I can find out. We are approaching lunchtime. I think I made this far too complicated. We just use what beta is. And this is a lattice, and this is a lattice, and gamma mark lies in gamma, even in gamma 1 of level n, and that maps, then it maps the lattice to itself. So that was trivial. Just wasn't able to see it, sorry about that. Now D. Here we must use certainly that we are in gamma 1 of level n. So let's use a basis where the first one is nt and the other one may be whatever it wants. So that's the basis. And then we will find what is nt mapped to. Oh, but we can work modulo n. It's 1 divided by n alpha Actually, when we have alpha and n, doesn't that mean that alpha gamma lies in delta n? Let's just take a look at that. Let's assume that. So alpha gamma, let's it have A, B, C, D, and we map it at 1.0. So it's A point C and modulo n. This is equivalent to 1 divided by n, 1.0. Which means it's 1/n of nt. That was a little weird. Oh yes, we shall see what no, it's still t. T is not being transformed. No, I'm confused again. So this was all wrong, because we are not asking what happens to nt when we transform it. We are asking what happens to nt in the Oh yeah, then we have to find the bases. The basis here, so let's just compute the one of the other. That's B point D. And B, we don't know, D is equivalent to 1. Well, there's the unity there. So we are basically asking 1/nth point naught. What is the order of that in the sky? That should not be a prerequisite. But you can see here, if capital N is 4 and minuscule n is 2, then it only has order 2, and it should have exact order 4. Yeah, I don't get it. A break. Hello again. It's now Wednesday morning, and I do have a little time to work on mathematics before I need to start packing. We're going on a holiday a few days to southern Jutland. But the first recording ended in confusion, and the way ahead then is to make an example of the theory, and a very simple one at best, because then you have a good chance of finding out where the misunderstanding lies, or whatever causes the confusion. And I chose that capital and minuscule n equals 2, and the most primitive lattice I can think of. And then I write up the definition of delta 2, C being even, and determinant 2. And then the thing I missed, I did read it, but then I forgot it again, was that A must be odd. For some reason I thought that delta 2 contained these two matrices, and it doesn't, because here A isn't odd. And that means that the side class, we must use S as well to get this matrix, so that we can get f of 2z. And this one will lead to f of z half plus f of z plus 1 half. So there was a confusion there. And I just discovered it while writing up this definition, that I had a misunderstanding there. And that means, I don't know how deep it's rooted, because I need to read the whole theory again. Because the side classes, I think I did them right, but I need to go through it again now that I have found out this. So that was a very short recording. Hello, it's now Monday morning and I'm back from the holiday and relaxed yesterday. So I think it's time to go on here. We shall at any rate rely heavily on the structure theorem of delta L, that is formula 528. So in this case, delta 2 of 2, what was that? Oh, that's unity. And Z is the disjoint junction of 1, 2, and 1, 2. Oh, here we shall, now I'm not applying this properly. It's, yeah, it's 1, 1, 2, right. So we need to see how our different choices of t operate in this. And one of the L marks is span 1. Oh yeah, we had to divide by 2, so that's actually, we are usually doing it in the opposite way when we are operating with, so let's go back to the usual way, so it's I.1. So it's like set point unity. There we go. And then it's I halves. Point 1. Or the other one is 1 plus I halves 1. And in this case, I halves, if we chose that as t, fails to have order 2. And in this case, it's of course 1 plus I halves. That was my problem, that in general, t wouldn't have order n in this guy. And that means my intuition was right. So when we talk about t, it's always understood that t is 1/nth. And the d's we get in this composition, we have to write it in general. So it was formula 528, I think. Yes. A disjoint junction of gamma 1 of n, and then this sigma A, and that's A in this multiplicative group, but also dividing n. So it's the divisors of n that are mutually prime with n. And then the matrices A, B, naught, D. That's a little weird. Where D is n divided by A. So let's choose a guy. No, the first thing we need to show is that T is still has order n in Lamarck. So we choose a guy in here. Let's call it. I don't know what to call it. It's too long ago I looked at the problem. So we take an alpha in this guy. Alpha equals gamma 1 sigma A and then we take is that gamma even relevant? Couldn't we just take the, because that gamma just gives an exchange of the annuit basis, so to speak. So why not just take 1n of alpha? 1/nth of alpha. Well, let's put a guy from gamma behind. I think that's a little odd. Why don't we just use 1 alpha? What does this gamma help us with anyway? That actually ruins my idea here. Because my point was that when gamma was unit, sorry about that, when gamma was a unit matrix, then it would have order n. Well, this makes my argument fall apart. So I thought I would be able to solve the problem, but it remains. So time to work on it by myself. Hello, May the 1st, Workers' Day. So let's work a little on problem 7. When I went through what I've made here, I said, did I really argue this? Because doing the examples I saw it work out, but I didn't know the reason why it would. But I did prove it, I see. All right. Now, I've come to the conclusion here that t must be proportional to the second coordinate. And that means that we must check how the second coordinate maps under alpha gamma. Did I say how it maps or connects? How it maps under alpha gamma. I would actually like this to be a member in delta n. So let's start to see if that's the case. So we have alpha lying in Mn, and we have gamma lying in gamma 1 of n. Hij, where h and k are equivalent to 1 modulo n, and capital N divides j. Because it lies in gamma n. Yeah, it's 1. It's here. All right. And we have the conditions on, well, the conditions of delta n here. No, that was the structure theorem, which is just a lemma in this book. Where do we have the conditions on M2? Here. So we just write n instead of 2, and a is equivalent to 1 modulo, modulo what? That's modulo 2, modulo n. There we go. And this is, of course, minuscule n. So just to make life easier for yourself, when you make examples, then choose like capital N being 4 and minuscule n 2 or something, so they are definitely different. Now, so I want to prove that it lies in here, and that means that AH plus BDA modulo n, A is 1, H is 1, B is whatever, and J is naught. That gives unity. And Ci plus dk, C is naught, and D and K Actually, there is no condition on the second coordinate. It's this one we have a condition on. C is naught and J is naught. And the last condition, that the determinant is equal to n, is obvious. So that was nice. That means that alpha gamma actually lies in Mn. We are still on D. So the second coordinate, let's just call it the number 1. And then we have a member of M2, of Mn, minuscule n. And the second coordinate and that's the second row. Now this is wrong. It's disagreeing with all we've done all through the I thought it should be C CZ plus D, that's what it gives. AZ plus B, CZ, right. So this is correct. And then I would like that to be proportional to 1. That means that B must be equivalent with naught modulo n, which it is not. Like we have a simple guy like 1, 1, 2. Well, maybe we should make both of them. No, that doesn't matter. Maybe it does. Maybe it does. So we have the 2. Now let's work with like complex numbers. So we call this I, the imaginary unit. And then we get something else here. We get, well, I call it Z. There's no, so it's AZ plus B point ZZ plus D. Shouldn't we divide by n, by the way? Yes, we must divide by n. what I would like is to go back to, so eliminate Z. To find a generator, or so to speak, on the real axis. No, that's not so to speak. That's actually a generator on the real axis. We multiply this by C and subtract this times D. BC minus D squared. We multiply X by C. It's by A. One can't read. AY minus AD, which is N. Or minus N, rather. Because this matrix lies in Mn, minuscule n. So that is on the... Oops, I forgot to divide by n. So it's actually minus 1. That means that we have 1 lies in L mark. Excellent. I almost said, then we are done, but when t is 1 divided by n, then it might be that n is 4 and 1/2 still lies in L mark. Well, I have made progress. And they must, of course, be of the form 1 divided by d. We can reduce it to a stem fraction. I believe that's what it's called. I don't know the term. Oh, it's not d. We need to find a new letter. Do anybody know a letter like M? All right. So we have to assume that 1 divided by m lie there, and then find conditions on m. That may happen if A and C have a common denominator. may that happen? A is equivalent to 1 modulo nm, and C is equivalent to naught modulo n. They are quite likely to have a common denominator. Example, n equals 2, C equals 6, and A equals 3. But, of course, this denominator cannot have a divisor that n has as well. And then we are home the same way they have argued in the book. So, I believe that finishes part D, which really had me confused. Here we operated from the left with gamma 1 and found out that that was really irrelevant in the beginning. It will probably be very relevant in the next. A one-to-one correspondence with right cosets. We'll just set the scene. So that's the second sentence. The first only took a fortnight. I don't know if we should skip this gamma, but let's write it. And then assume that well, putting a gamma in ahead then this is L mark, so it's that's weird. But this of course is equal to L mark itself, because we are just changing the basis, so to speak. So no problem. The inverse of gamma mark will bring it back. So that's obvious. So operating with using gamma mark alpha instead of gamma mark doesn't change the lattice. And next, assume L mark equals 1 divided by n alpha gamma L and beta gamma L. This is L itself. Now what was that? We operate on both sides, so that's gone. And that means that alpha to minus first beta lies in gamma. That's the definition. So beta equals some gamma times alpha. Now we have to show that it's in gamma 1. I'm a little confused here because it seems trivial and it shouldn't be. Oh, I don't understand the question. Mind you, alpha lies in delta n. Yeah. Oh, I called it mn, didn't I? Yeah, here, that should be a delta, like I wrote here. And here I didn't commit that error. Then it's very, very very necessary to think, because if this is only in gamma, where alpha lies in delta n. I've only shown that if it was gamma 1 of n let us check if we multiply by any element of, so the determinant is obviously minuscule n. And the first coordinate a may be anything, but modular nh is unity. So that doesn't hold. Now how about the dividing here? That fails as well. So this doesn't work. Aha! Maybe this is where the gamma comes in, though I can't see how. Well, I must drum up an example of now we did have this the same It's not. Didn't I almost prove that any matrix? No, they had to be in delta n. I just have to think this through, and then we'll carry on. Right after I turned off recording, it occurred to me that I hadn't used the fact that alpha and beta both lies in Mn, or delta n, sorry. So let's go ahead and do that. As I pointed out, the determinant of this guy is unity. But now if alpha is A, B, C, D, I think we already had that. What was it? N squared, alpha to minus first, lies in delta n 2. Wasn't that what we had up here? Oh, I didn't actually prove it. So maybe I did that somewhere else. We'll just check it. The determinant is n, so it's 1 divided by n. Oh, it's only n, of course. And then dA minus cb. No, it doesn't. This one is equivalent to 1, not this one. dH minus ck di plus bi plus and minus ch plus ak and minus ci plus al. And modulo n A is unity, H is unity, C is naught, C is naught, K is naught, D is unity times I plus, this doesn't matter really, but this minus naught plus 1 times L one naught, and that's actually the definition. No, it needed to lie in I want it to lie in gamma 1 of n, and that means that now that's very weird. The determinant of this guy is 1. there's something very wrong here. We'll just put it on the afterburner and see what I can think of. And then let's get started with the last thing. We should use what we've found on formula 5.9, where the definition of Tn on a modular function on the lattice and on the modular point is defined. This is the definition, and here we use the result I haven't yet proven. And that translate that to f of z and then the span of z.1 O we actually already have a formula for this in the book. Already they did compute that, so I'll just make a break and then see what it is. The formula I thought about was on top of page 160. And I'll just write up what it says. And then gamma of z over 1, they take it as a vector, all right. Then it should have been tilde, of course, but never mind. This only confuses me more. This doesn't help at all. We shall need the to write f over to f of yes, f of gamma z. That because they are considered an example where C vanishes. Well, we'll have to do it myself. Yes, I wanted to say we'll have to do it by ourselves, but then I'm like the one doing it. And then this must still have order n in this lattice. So we can take cz divided by plus d outside the parenthesis. Guess that's to the kth. And that's just f of z gamma k. There is a little question we have here, because it's cz plus d. We get up, oh, it should be divided by cz plus d. I don't know really what I'm dealing with here. Or maybe I have a misrecollection. Well, on the other hand, if we can do this, oh, we have an n here. I forgot the minuscule n. Maybe we can just let gamma be alpha divided by n here. And then take it out afterwards, because it doesn't change the operation here. It just gives this factor n to minus k first. Now this should be here, n to minus k first, and then k first, that's k halves, and then minus 1 from 1 divided by n, f of z alpha. I will just erase this guy. Alpha is just alpha k. And that should be 529. No. Oh, I was... 527, and it is indeed so. That means that this definition, modular this problem, is equivalent with 5,9, which we had there. So I have one problem here. We'll just mark it in magenta. And one question here, which I didn't quite prove this to hold. That's the last remaining problems. Hello, I've now been to tennis, still May the 1st. I just wanted to see if I could finish this. The first thing is that this is a confusion. F tilde only takes the vector, meaning this is not a problem. Right. Next, for the guys here, so we assume that alpha L equals beta L, where alpha and beta lies in delta n of m that means that now what I'm thinking about here, the point is that the right side classes must agree. And that means that, or is equivalent to beta alpha to minus first lies in, there should be gamma 1 of f, of course. Now that was not what I ended up with here. But what we get from here is that alpha to minus first beta has integer coefficients because it's in gamma. And then we should be able to show that, but we couldn't. But on the other hand, this is what we must show. So can't I reduce it that this actually has integer coefficients? Well, let's get on from there and then leave that for a while. So we write alpha and which is equivalent to 1 naught modulo n, and beta hij also being equivalent to 1 naught and then I would like to know that this has integer coefficients, because alpha to minus first is 1 nth of dA minus C minus B, and that means that beta alpha inverse equals 1 divided by n, and beta hij d minus b minus ca and it's only the first terms we need. So h is equivalent to 1, d is actually equivalent to n, because the determinant is minuscule n. That's times I is whatever, but c is equivalent to naught. And j is equivalent to naught. Minus k is n, and c is equivalent to naught. All right. Oh, we have to show that this lies in gamma 1, so we need to show that this one is irrelevant. Minus j, that's naught, times b, plus k, that's n, times a, which is 1. We have to continue up here. This gives n divided by n, that's unity, don't care, naught, and n divided by n, that's unity. So it is actually in gamma 1 of n. The only thing I'm having trouble with, that's showing that this guy actually lies in gamma, that it has integer coefficients. We know, of course, that the determinant is unity. I need a little space to write. So we have alpha L equals beta L, and they operate on L from the left. If we call this L mark, then we have alpha, the reciprocal of alpha times L mark equals the reciprocal of beta times L mark, and then we operate with beta on both sides. Beta alpha to minus first L mark equals L mark. I've got it. That implies that it is a repositioning of the basis. So beta alpha to the minus first lies in gamma. I think I have finally solved this problem. It has also taken quite a while, but then I've been busy as well, and some days tired. But I needed to clear up a lot of stuff, and I must say I had a few misunderstandings. That was the things I needed to clear up, of course. Cheers.